morning, everyone. Thank you for joining EAC's webinar today. This is Addison Tyne. I am the marketing specialist here at EAC. We will be recording the session today, so pending any technical difficulties, everyone will receive a replay of the webinar. Please feel free to drop any questions in the queue and we will get to them after the presentation. Following the session today, a short survey will appear, so please stick around and answer these questions after the webinar. Today, I will start off with a short introduction of EAC, and then our technical account manager and Creo expert, Bill Schlen, will be showing us how to improve assembly performance using an enhanced top-down design process for faster, easier designs in Creo. At EAC, our mission is to transform the way companies design, manufacture, connect to, and service their products. We are located all over the US, and our headquarters are currently established in Minneapolis. We are more than just a value-added reseller for PTC, though. For over 20 years, we have helped companies innovate their product development processes. With experts in over 22 different areas of product development, we help organizations create better products, rethink what may seem impossible, and ultimately achieve results that make a lasting impact on the world as we know it today. Beyond helping organizations connect to the information they need, we also work with companies to connect their enterprises, as well as specific focal points which produce bits and pieces of their operational value. We also assist with design and engineering products, host educational webinars, and PTC certified training courses. Aside from that, we have partnered with Formlabs, which allows us to offer our customers some of the latest and most affordable 3D printing options in the industry. All in all, we want you to know that EAC is a company to get all the technology at the forefront of your business to help make your team successful. Our niche is helping you figure out where to start. Our specialty is helping you build on what you already have. With that, I'm sure you've heard enough of me for now, so I will go ahead and hand things over to Bill so we can learn more about the different top-down modeling methodologies available in Creo.
Thanks, Addison. Hello, everybody. Today, we're going to talk about skeletons. And this is different than a lot of the presentations I do where I spend a lot of time in Creo showing different techniques and things like that. Today, it's more of a philosophical discussion, although we will be working with the software, obviously. But I'm going to make the assumption that everybody has a handle on really what a skeleton is. But I'll spend a couple slides just talking about it briefly, and then we'll get into really their use. So a skeleton is really used to set the intent of a design and control the references. And there's really two types of skeletons. There's a standard skeleton and a motion skeleton. We're going to basically talk about standard skeletons today. A skeleton part is like any other part. It has layers, has relations. You can have family tables, simplified reps, things like that. As you can see from the slide below, a skeleton could be as simple as a coordinate system, or it could be as complex as an engine block, or anywhere in between. But its idea is to really change the way that parts reference one another or reference the assembly and try to refine that so that they reference the skeleton. This makes it a lot more transportable and a lot more easier to control. So some important considerations to think about. First of all, you can only have one motion skeleton in an assembly, but you can have multiple standard skeletons in an assembly. There's a config option. By default, it's set to no, but if you set multiple skeletons allowed, yes, you can have Maybe another way of working with this is to put the skeleton at the top and have the subassemblies reference that skeleton, and then all the parts reference the skeleton assembled into those subassemblies. Again, all these skeletons are identical, so they do have or can have more information in them than what the subassembly 2 needs, because it has information in there that 1 has. But again, it's a real simple technique to use to kind of control the referencing of parts. Then we have multiple skeletons. So in that particular case, you have a unique skeleton for each subassembly. When we put in multiple skeletons that are all unique, we put one under each subassembly. And then that has the unique characteristics that only that particular subassembly would need. Maybe another way of looking at this would be, I'm going to create a skeleton assembly. Now, there isn't really a model type or file type called skeleton assembly, but what you do is you just create an empty assembly, and then you put the skeleton parts in it. So in this particular example, this skeleton assembly, or basically it's just a regular assembly, it's just a holder. It's like a bucket holding various skeleton parts that I'm going to use in my top level assembly. And then those individual skeletons are then assembled into each individual subassembly. So just kind of a different way of organizing things. A little bit more elegant, maybe, doing it this way by placing them all under an assembly there, so we can have kind of one-stop shopping where we know to look for all the skeletons that we may need. The next one, as you know, is hauntingly similar to what we just saw. It's called a skeleton assembly. It's the same approach where each subassembly gets unique skeletons for it, but it extends that multiple skeleton approach by, in this case, these unique skeletons are in a skeleton assembly, but their locations and their orientations are important, right? So we're basically making an assembly of skeletons, and they're all assembled in the correct location and orientations that they would need to be in the assembly if they had parts in them. And then again, we just assemble each one of those skeletons into the individual sub-assemblies. The final technique is called the Hangar Map Method. And this is kind of the old school way, right? And even some of the NX guys still work like this, where in this case, we might have a series of coordinate systems. Here I have a skeleton with coordinate systems on it. But then what we do is when we assemble our parts is we just say, I want the part coordinate system to align with the skeleton coordinate location. And we're just basically hanging the parts on these coordinate systems. You don't have to use coordinate systems. You could use datum planes and things like that. But to keep it simple, if you use coordinate systems, that's probably its biggest advantage, is that it's simplistic. So now that we've talked about these 4 different techniques, you want to start to think about really what do you want to accomplish with your skeletons? Which one of these techniques do I use? What are the objectives of my particular assembly or product that I'm working with? So there's a couple things that we want to look at. First of all, we want to look at reducing complexity. And that just means that we want to minimize component interfaces to the top assembly, right? So we want to kind of shield those components from the top assembly using the skeleton as an insulator. Second, we want to simplify the modeling effort. So again, we want to reduce external references, not only between components, but also to the assembly itself. We also want to increase design flexibility. Does it support changes to the interfaces of those subassemblies, or can we easily change those? And can we easily change maybe space claims for those subassemblies? And then we also want to think about large assembly management, right? So does it allow for modularization of the top level assembly? Can you break down the top level assembly into various components? And then does this particular approach allow for the control and sharing of common information? So even though we might have different skeletons, we might want to pass information between them. It could be parameter information, it could be relations, things like that. So we still can pass things between skeletons. Does this approach that we're going to use allow for that type of passing of information intra-skeleton, if you will? Finally, or not finally, but do we want to maximize reusability? So do the skeleton structures support the reuse of sub-assemblies without external references to the original assembly? And then can we increase visibility? And by visibility, I mean, is it easy to understand the skeleton? Can you improve the readability of it? And also understanding what data is shared between skeletons. And then finally, does it support collaboration between teams? Usually if we have a larger company with large products, we kind of break it down into different design teams. Do these structures allow these teams to work independently and still share critical information? So these are things to consider when we're trying to define and decide on what type of skeleton approach to take. So let's look a little bit more deep into each of those 4 techniques and kind of the pros and cons of those. So the single skeleton is created at the top level assembly, and then you can assemble it into each subassembly. This technique is best used for assemblies that don't have a lot of components. And it really isn't good for use between multiple teams that shouldn't have access to everything, because everything is in one skeleton. Every team gets exposed to the information in all the skeletons. And maybe that's more than what they need, right, technically. Also, they're difficult to reuse because they reference the top level assembly. If we want to pull that out and maybe use it in another location, because of those references, it's kind of hard to reuse it. It's usually best for products or assemblies that have unique subassemblies. And that way we're not reusing a subassembly at all. Every subassembly is unique, so we don't have to worry about the inability to kind of reuse things easily. The next thing we'll talk about is multiple skeletons. Well, let's take a look at a single example of a single skeleton first. So I have Creo up, and here's an assembly. This is an old Creo assembly from the old days, but what we have here is I've taken the motor, the block of the motor, and that's really the skeleton. So here's my skeleton. What I've done is I basically used the old master model technique. What I did is I created a skeleton, and then I said merge in the motor block. And when it brings it in, it doesn't bring it in as a solid, but it brings it in as a quilt. And when we talk about skeletons, I kind of look at them from the standpoint of they do one of 2 things usually. They provide locations where things should be mounted, and it also can provide an envelope on where things should fit inside or fit outside of. In this particular example, this skeleton, the reason I used it as a skeleton is because it has both. So I could have easily made this skeleton with, a couple of axes here where the mounting hardware would be, and a couple more down here, maybe a cylinder to represent where the sleeve would be for the piston, and then maybe some internal surfaces for where the crank needs to go and an axis down the middle and things like that. And that would be a pretty simple skeleton. In this particular case, though, the skeleton not only has all the locations of where I should mount things, but it's also being used as an envelope for all the internals of this. So now the piston knows where it should fit and how it should fit in this particular motor block. The same with the piston rod and the crank and things like that. So this particular skeleton is being used both as an envelope part and as a reference for mounting. As you can see, it can be pretty complex, right, compared to a couple of coordinate systems and some axes and planes and surfaces that I could have used. But again, in this example, this is actually a really good technique for something like this, where this particular skeleton, I'm mounting everything to it. They all kind of use the same skeleton information. Every one of these assemblies uses this skeleton. So let's go back and let's talk about multiple skeletons. So that's really where we have a skeleton, a unique skeleton in each subassembly. The design information of the entire product is split up, right, between the subassemblies. Skeletons can be referenced across a wide range of subassemblies. So we can break the information up into a variety of different subassemblies, and then if we have a larger company, we can part out those skeleton subassemblies to the other groups that would be designing this. So it's a really good technique for breaking down the information into unique packets and then distributing that to the different design groups that are there. So let's look at an example of this. So here's an example of multiple skeletons. Here I have a framework, and I have 3 cabinets that this framework supports. Each cabinet is totally unique. It doesn't interface with the other cabinet, other than the fact that it might be next to it. But all the components that go in it, these are space claims that I'm using these skeletons as. But each subassembly or cabinet in this case is unique. So the components that go in it are unique. Its function is unique. So it's a really good reason to use multiple skeletons. So here I have just 3 skeletons out here in our grid sitting at the top. Whenever you create a skeleton, first of all, in an assembly, it automatically moves it to the top. You can create it whenever you want, but it will always move it to the top. If you assemble a skeleton into an assembly that doesn't have a skeleton, it automatically assembles it at the top at 0, 0. Any skeleton after that, you can assemble like any other skeleton or any other part with mates and aligns and offsets and things like that. But here I have those 3 unique cabinets, right? The left cabinet, the middle cabinet, and the right cabinet. And I've taken those skeletons and I've assembled them into each subassembly. So here's the subassembly for the cabinet, who has the left cabinet space claim for the left cabinet skeleton. And then here we have one for the middle, and then also one for the right. So all I'm doing is just taking these skeletons and assembling them into the subassembly, and then I can part out those subassemblies to various groups, and they can start to design, in this case, within the bounds of the envelope parts that I've created here as skeletons. Let's take a look at the next one is the skeleton assembly. This is real similar to what we saw here, but it's a little bit different. I'm going to go through this one a little bit in more depth because there's a little bit more to it. But a skeleton assembly actually extends the multiple skeleton approach by adding the skeleton organization in terms of an assembly, and those individual skeletons are assembled in orientations and locations that the actual subassemblies would be in. So this is really useful for large assemblies with many unique components developed by multiple teams. Subassembly references are only applicable to the skeleton that is in that subassembly, which makes it very easy to reuse those subassemblies and those parts that reference those. Because they're only referencing skeletons, it's easy to pull them out and use them elsewhere. So let's look at an example of this. So in this particular example, this is a computer. And what I'm looking at here is the top level skeleton assembly. So what I did is I just created an assembly, and then I started assembling skeleton parts into it. So the main skeleton portion is really the outer box of this desktop computer. The next assembly that I assembled in is right here. This is the power supply. So the power supply just has space claim in it, right? So anything I create for the power supply goes inside of that volume. And then finally, I created something for the graphics card. And basically, this is a simple subassembly that has a coordinate system where the graphics card is. Right? So you notice that these skeletons are located in the main skeleton in their actual positions. And this is going to become important in a second here. So I'm going to close out this skeleton assembly, and we're going to look at the top level computer assembly with the skeleton assembly assembled in it, right? So here's the top level computer assembly with our skeleton assemblies right here assembled in that we saw before. So now I can start to add and actually kind of part out these things. So the first thing that I would do, I'm going to open up, let's say for the power supply, that subassembly. So I can copy, right, this power supply into, create a subassembly for the power supply, put the skeleton part in it, and give it to the power supply guys to develop that. So when they do that, I'm going to go over here and say, let's get the power supply assembly. I'll say, let's open that up. So here it is. Here's that skeleton. Right? And what I'm going to do, so this is what's different about this, is I'm going to now assemble this. So I'm going to say take, and I'm using the skeleton in the subassembly and assembling it to the skeleton in the top level assembly. So I'm actually kind of assembling the skeleton to itself. So I'm going to say take this coordinate system and align it with this one. So now in this particular example, when I added this subassembly in here for our part, I'm going to say let's hide our skeleton here and let's turn on the part that we have for that. So here's the part. It sits inside that skeleton. Because the part fit inside the volume was assembly or correctly assembled into the top level assembly. Everything works out good. Same thing with the graphics card. So in this case, I'm going to say, let's take the subassembly for the graphics card. We're going to, whoop, not this guy, we got to cancel this. Let's go in and assemble in the graphics card. So here's the graphics card. And again, I'm going to use that coordinate system. So I could come over here and say, let's take this graphics coordinate system here and assemble it to this one. This brings in, and in this particular case, what I did for a little kind of subskeleton in here is I just put a plane in here. And this represents kind of the board itself, the size of the board and the location of the board. But now I can start assembling the real geometry onto that. And so what we can see from this, if I go in and turn on the components once they have been created, I'll say let's turn this guy on. We can see that we now have the graphics card assembled in the correct location. And all of these reference skeletons, it's very easy for me to pull this graphics card out with its skeleton and assemble it somewhere else. So let's go back, talk about the next one is the Hangar Map Method. So this is used for more or less kind of a bottom-up approach where you only want the component's location. Really, that's really the most important thing. Not that they're touching each other or they're mated together or anything like that. It's just we want to place them real quickly and easily. So it's easy to assemble components in this with this approach. And all locations, in this particular example, and examples I'm using a coordinate system, and technically that's usually what people think of when they're talking about the Hangar Map Method. I mean, I'm going to place a subassembly in, but I'm just going to place it using a coordinate system. Real simple. But you could use datum planes in your skeleton and assemble it that way, should you choose to do that. So again, for this one, let's take a look at working with that. Here I have a top-level assembly. I put a skeleton in there. The skeleton just has a couple of curves here and then some coordinate systems for placing parts. So if I want to assemble my parts in here, I just go in and I'll say, let's grab maybe the arm part. I can place that over here. I'll just say, let's take this coordinate system and assemble it to the arm coordinate system. So first part's in. Let's assemble in, let's say the boom. So here's the boom. I can say, let's take his coordinate system and we assemble it to the coordinate system for the boom. And we notice that it's all oriented correctly, so things line up. And then finally, let's go in and say, let's assemble in, I don't know, like the main body of this guy. Again, I can place him here. I could say, let's take body coordinate system here. And you know, this guy has a coordinate system on him somewhere. There, he's automatically placed. And so this is kind of a kid's toy, but you can see basically kind of an excavator. But it's really easy for me to put components in there, and they're totally independent of one another, right? They're only looking for their coordinate system, which happens to be on our skeleton here. So now that we've talked about the different methods, and there are different pros and cons to these methods, right, that we kind of talked about, and you don't remember anything that I told you, but let's go in and kind of rate those, right? So now we're going to look at each of the 4 techniques I talked about and how they influence those objectives that we wanted. You know, is it easily visible? Is it good for large assembly management? Is it good for reducing skeleton complexity? And so they have different ratings. 2 pluses means it's positive in a good fashion. 1 plus is, you know, it's pretty positive. 0 means has no influence, one or the other. Then there's a 1 minus sign is a negative influence, and then 2 minus signs, really negative. So for the single skeleton, we can say reducing complexity, not really because everything has to be in that one skeleton, but for simplifying the modeling effort, it's easy because there's just one skeleton I got to worry about. But increasing flexibility, no, because everybody uses the same skeleton. It's hard to reuse them for the reasons I talked about. The visibility is pretty simple and straightforward. That's a positive because everything we need is in that skeleton. So if we look at that, we can kind of see what's going on. So same with multiple skeletons. You can see that that is a little bit positive or a little bit negative, depending on what type of thing you're looking for. The skeleton assembly seems to be, even though it's the hardest one to work with, right? Because we're creating this assembly of skeletons and they're all located in the correct positions, it has a lot of benefits almost through everything other than simplifying the modeling effort, right? Because we had to make this skeleton assembly and make sure everything assembles correctly that way. And then the hanger map, it really doesn't, it's kind of very neutral, right? It's really good from the standpoint of reducing complexity because, you know, we're just assembling coordinate systems. Everything else, it doesn't really hurt or help really too much. And it helps a little bit with increasing design flexibility, but because we can move the coordinate systems around rather easily, and you know, obviously that moves the components themselves. So these are kind of the ratings that we put for these different techniques. So depending on the type of product you're creating, the type of groups that might be working on that product, really how you want to organize the referencing of components to one another or not. We kind of look at these different techniques and try to decide which one is the best. So that kind of brings me to the end of our talk today. There's a lot of more philosophy in there, but this is actually a pretty useful graph here, I think, to kind of tell you with the different techniques which one might be best for you. I can't tell you that, right? You know best yourself, but hopefully, you know, the whole idea of this is to help you make better decisions. So with that, I'm going to turn this back to Addison.
Awesome. Thanks, Bill. I don't see any questions in the queue. I want to thank everyone for taking the time to join us today. If you have any additional comments or questions, please feel free to reach out to me. I have included my email in the chat section of the webinar today. Next week, we will be wrapping up the Creo series with the Design Exploration Extension and how the combination with Creo Simulation Live can really speed up your design process. I'll provide a link to that in the follow-up email being sent out this afternoon. To wrap things up this morning, another